Okay, so let me get these homeworks passed out first, and then we'll go ahead and get started. I'll see if anybody has any homework questions. Kind of pinned in here. I'll go this way. Excuse me. Josh. Sergey. No, I'm just gonna go over there's a review and and I'll suggest some good problems to look over. I don't know, did I do the chapter 2 review already? Yeah. Amanda? Sally? Chloe? Scott? Reese?
Gotcha.
Abel? Len? But yeah, I'll say something about that in a second, Sergey. Okay, so Sergey was wondering if there's going to be a like a practice test or anything like that. I'm not going to make a practice test. So what I did was I posted the suggested textbook review exercises. So I have suggested exercises for each section, and then also there's a chapter review. And rather than actually make a new practice test, that's your practice test. Okay, so I've suggested some good problems from there that I think you should be able to do for the test. Usually I don't like to be too tricky, right? I can't really come up with problems that are that much different than what I've suggested in the review exercises or in each section individually. Okay, so it should be fine there. I might get that, if it's not too long, I'll print that review off and I'll bring it with me tomorrow or Friday. Okay, so the test will be on Monday. Most likely I'll print that review off tomorrow, so just to save you some time printing it off on your own. And then on Friday we'll go over some of that, and then I think I already said I'll be coming in on Saturday from 2 to, I'll be here till at least 4, but I should be able to stay till 4:30 or 5. Okay? If there's still people here at 4 and that have questions, I will stick around till 5. Okay, so Saturday, 2 to 5 in this room. Okay. And then Friday will be a review, and then Monday we'll have the exam. Okay. I'll also be in the TLC. I'll probably stick around on Friday too. After class, I'll stick around in the TLC for a couple extra hours as well. Okay. All right. Anybody have any homework questions, conceptual questions before we get started? Yeah? No?
Number 9 on online homework went over endpoints.
Yeah, I got it stuck on.
Oh. Well, let me take a look at it because I might have overlooked something, so let me see if we can do that real quick.
The first 2 parts of the problem weren't hard, it was just the endpoints, part C.
Okay, let me take a look there. Number 9 on the online?
Yeah.
Okay. Oops, that's not the right password. Another thing I want to mention is, for some reason, my Outlook was disconnected. It was offline. So I haven't been seeing my emails for the last day and a half. I did get it fixed, so I should see everything now. But there was a few people that had sent me some emails. I think I did get back, but if you needed some extra time on the homework because I didn't get back to you in time, just send me another email or Canvas message, and I can work that out with you. Okay. So this is the which homework? 2.7? Okay. And that was the last question, and it says, oh, okay, the break-even points. Okay, so that's the same question you had too, then. Okay, so it gives you, and my numbers might be different than yours, but they give me a price function in terms of the units demanded, 22 minus square root of x. And then they give me a cost function, which was 371 plus 4x. So I don't know if everybody had different numbers. Sometimes my math lab problem generates different numbers for different students. And then A was you're supposed to write the revenue function as a function of x, and then you're supposed to graph the cost and revenue function in the same viewing window. And that for that were you able to use like Desmos or something to at least pick the right graphs? Because let me see what they do. I'm going to get the first problem wrong a couple times here so I can skip to the next one. Yeah, so you had to choose the right graphs. So for that, maybe I could spend a minute actually talking about how to do this in Desmos too. Was that a problem to actually plot the graphs in Desmos too? Okay, so maybe let me get the projector turned on and I'll show you how to do that as well first. Oh yeah, it's this one. There we go. And then they have a little cord connectee. Yeah. Alright. Do they have that little HDMI thing laying anywhere? I wonder if it's the same one that's over here. Hopefully I can reach this far without sliding the camera off the cable. I can't. Let me just pause my video for a second. Or I'll go back to technology frustrates
Can
me
we
sometimes.
slide this?
Yeah, let's try just sliding this for a second. Okay. There we go. All right. And then I have to do this. I think here's what I have to do. Okay, I'm sorry, but when you go into Desmos, here's your screen, right? And then over here you enter the functions or whatever. There's a little toolbar up here with some little wrench or something like that. You're going to click on that wrench, and then you can change the viewing window by picking the x coordinates and the y coordinates. Okay, that's the best I can do because I can't get this really to work right now. Okay, so you can change your viewing window. Again, there's some little wrench that you can click on in the upper right corner on Desmos. And then you put the equations over here, click on the little wrench, and you should be able to type in the x values of the viewing window that they give you on the problem. Okay. And then you won't be able to solve this equation or find the break-even points using Desmos, I don't think. But I'll kind of tell you where you can go to do it. Again, I don't really know why none of this is working, unless it's because I unplugged this. I can try this one more time. I don't know why they haven't just fixed this projector yet. This is frustrating. Okay, there we go. So maybe now I can get this to work. Okay, so we're going to go laptop. Let's see if I can do this. It's not letting me do this at all. Let's see what happens. This isn't working either. Come on. Crossing my fingers here. Still a blue screen. Maybe I have to switch it to PC. Well, okay, we gotta go old school. Okay, so anyways, let me. Okay, so that fixes the viewing window thing. If you just go into Desmos, you can enter each equation, the revenue and the cost, and then click on the little wrench, you can change your viewing window. Okay. And then if you do this, you had to do this problem, I think you had to solve for, actually you didn't have to solve for anything. The revenue function is just going to be the price times quantity. So you do x times 22 minus square root of x. You get 22x minus x times x to the 1/2. So is everybody comfortable with a square root can be rewritten as a 1/2 power? And then when you multiply things with the same base, you add their exponents. 1 plus 1/2, I believe, gives you 3/2. Okay, so there's the revenue function, here's the cost function. So you take each of these equations and you're going to plug them in the equation box in Desmos. And then you can change the viewing window by clicking on the wrench and then just match it up with the correct graph that they give you. Okay, so part A was no problem. And then for the other part, the break-even point, you'd have to solve where your revenue and cost function are the same. Okay? When you're selling a commodity, you break even when revenue and the money coming in and the money going out are the same. So you're going to solve the equation 22x minus x to the 3/2 equals 371 plus 4x. And then some of you might have a graphing calculator. If you don't, here's what I suggest you do. Go to wolframalpha.com. Okay. And then what you're going to do on Wolfram Alpha, they're going to have a little box for you right at the top of the page. You're going to, in that box, type solve, and then you're going to enter this equation. 22x minus x caret 3/2. So I'm going to show you all the parentheses and everything that you need. So the 22x, no problem, and then you can subtract x. To get a power, you have to do the caret, or the little upward hat button. And then if you have a fractional exponent, you need to put it in parentheses. And then the right-hand side should be no problem. You should be able to just type equals 371 plus 4x. Okay. And that should give you the solutions to this, which would give you the break-even points. Okay, and sorry for the technology stuff. I'll have to come up here and try and figure out how to get this connected to my laptop. But I kind of just, I falsely assumed that it would just all be set up and be working, but apparently it's not, so I apologize for that. Okay, so I'll, at the very least, if I need to, I'll extend this homework till tomorrow, like early afternoon. Tomorrow morning I'll come up here and I'll try and figure out how to get this to work, so then I can show you this formula. Okay. Alright. So does that help to kind of give a start, or? Okay. Hopefully, yeah, Missy?
So this is due today then? Or is it tomorrow?
If you need extra time, email me and I'll extend it for you. Okay, but I'm going to keep it due today. Now, I shouldn't say this. I don't think it's going to be that hard to go to a website, and I literally just told you what to type in and what it would look like on the keyboard. And then you hit enter, and then it spits out the solutions for you. Okay,
So you're going to move 2.7 to tomorrow then?
it already is due tomorrow.
Oh, okay.
So actually, I was confused by your question. Yeah. So let me double check for everybody. If I go to the announcement manager, it says 2.7 due Thursday, April 19th. So I switched it this morning. And if I go click on the online homework, it says 2.7. Okay, that, yeah, I didn't change that. So let me fix that right now. So now the online is due on the 19th. So my bad, I was wrong about that. Kind of had a bad day so far. Like, This morning in my pre-calc class, I had recorded a video for the class, and then I accidentally closed it without saving before uploading it. So, and then I spent like 30 minutes trying to figure out, trying to recover it, and that was time I could have spent grading, and I could have made a video by hand in 30 minutes. So, and it's just kind of thrown me off for this. So, anyways, though, that's kind of a me problem. Okay, so let me get this set back up. So what we're going to do today and tomorrow, if there's no other questions other than that one about how to find something that helps you find the break-even points, I want to spend, and I might just have to spend the rest of the day kind of doing this. We might get into some calculus in the last 10-15 minutes. Section 3.1 is just about exponentials and compound interest. Okay, so I'm not going to actually formally cover that section and teach it. 3.2, and I'll pass this out to everybody. And just start passing some of these around in this direction. And then I don't know if you can reach behind you, Amanda. Here's a few for over here. One of those days. Okay. Okay, so we're going to spend the first part of class just reviewing exponential and logarithmic properties and identities. Once I do that, we're going to hopefully, if I have time, we'll start talking about derivatives of exponential functions. Now, when you read through the textbook, there's also parts in there where they talk about derivatives of logarithmic functions, but what I've done is I'm going to put that on hold for now. Most of the time, the only times that logarithms really show up are in like chemistry applications or in maybe social sciences or population applications. So the reason I'm going to just do functions, that should say exponential functions, the reason I'm just going to do the exponentials for now is because all of our business models only involve exponential functions. They don't have logarithms. If it turns out we need logarithms for anything later, I'll just go back and do this section again and cover the other half. Okay. So we're going to review a little bit about what the properties of exponential functions are. And then to solve exponential equations, you need some logarithmic properties. Okay, so we'll talk first. And again, I didn't leave any room on this for the handout, so you might want to get the handout's just for the calculus part. So properties of exponentials, or properties of exponents. Now we've already used some of these before, so these shouldn't be anything really new. So first of all, the basic one is multiplying things with the same base. I think we actually just used it a second ago. You always add their exponents. Okay. And then the other direction works too. If I have a sum or difference in the exponent, I can split it up into a product of two exponentials. Okay. There's also one where if you take a to the n divided by a to the m, that becomes a to the n minus m. I don't really use that property that much. Usually what I do is I just take what's in the denominator and bring it up top with a negative exponent, and then I combine them. That's actually how you prove this identity anyways. Let's see, so you've got the sum rule, you've got the product rule, the quotient rule, raising a power to a power. Anybody remember the rule here? Okay, so in this case, the adding's for when you multiply two things with the same base. If you raise a power to a power, you multiply exponents. Other ones are a to the minus n is 1 over a to the positive n. So, and I think we've kind of used that one before too. If you have something that's a negative exponent, you can write its reciprocal and just change the sign on the power. And then the very last one that I think we'll need So say you have negative exponents on top and bottom. B to the minus n can come into the numerator as b to the n. A to the minus n can go into the denominator as a to the positive n. And ultimately, I think those are all the exponential identities we would need. So there's properties of exponents, and then you have properties of logarithms. Okay. And again, for us, we'll learn about the derivatives of exponential functions, but we're not going to cover derivatives of logarithmic functions. But we do need their properties to be able to solve some equations. Okay, so we've got the basic log base b of a product, and I'll tell you what these equal in a second. You have log base b of a quotient, and then the other one is log base b of a number to a power. And let me grab a stronger marker here. Okay, so anybody remember any of these off the top of their head? I'll give them to you if not. Yeah, if it's been a while. So if you do log base b of a product, it becomes a sum of logarithms. So you can do log base b of the first number plus log base b of the second value in the product. Okay, so log of a product. And this works for any base. And I might have to talk about how to calculate logarithms too in just a minute if I need to. If you have log base b of a quotient, it becomes a difference of logs. So log base b of the numerator minus log base b of the denominator. And these properties work in both directions. You can split apart a log, or you can put a sum or difference of two logs back together. And then the last one says, if you do log of a particular base of an exponential expression, the power can come out front and be multiplied by log base b of a. So you've got properties of exponents, properties of logarithms, and then you actually have some inverse properties. So logarithms and exponential functions are inverses of each other. Okay. The first one is if you do log of a particular base and do an exponential with the same base, you just get the power x back. If you do the exponential first, raised to log base b of a number, you get the input of the log back, as long as the bases are the same. And then let me see, do I have any more? I think that's going to be all we're going to need. Probably, and then some. Okay. And then what I can talk about is and I think in this section we're only going to need to know continuously compounded interest. So the setup here is you make some deposit at a certain continuous annual interest rate, and there's a function that gives you the balance after a certain number of years. So what we say is if $P is invested into an account earning, let's say this, into an account at a rate R, compounded continuously, the balance after T years is given by, so I'll use capital B for the function, your balance after t years is going to be PE to the RT. Anybody know why we use capital P? Your initial investment is sometimes called the principal. So that's where capital P comes from. And then the power is up here in the exponent, that's R. And then E, just so everybody knows, some people call this Euler's number. Okay. That's why they chose E. Leonhard Euler discovered it back in the 1700s. Okay. And that's the number 2.71828. Actually, I'm just going to write equals. And then there's a bunch of decimals or digits that I don't remember by hand, on the top of my head. I only know the first 5 digits. Okay. So usually P is given. E is just Euler's number 2.71828. The rate is usually given. The T up here is just the number of years that have passed, and then plugging in a particular value is going to give you the balance after a certain number of years. So I'll do one example, okay, and then we'll get into the calculus. So we've got all these properties of exponents. If I need to use one in particular, what I'll go ahead and do is I'll just rewrite some of these properties if we need to use them. Okay. So we'll do one example, and then we'll start talking about derivatives of exponentials. One thing you'd like to know, so a little bit of why we care, is say I can model the balance after t years with a function like this if interest is compounded continuously. That just means that the interest is compounded all the time. So every instant, you're getting interest on your balance the previous instant, and that just keeps happening. So say you did have a function for your balance, you might want to know at what rate is your balance increasing at a particular time. Okay, there's going to be times, like certainly after, like when many years have elapsed, your balance is going to increase at a higher rate than early on in the investment. Okay, because of the exponential nature. Okay, so the farther out you go in time, the faster your balance is going to be increasing. Okay, so our ultimate goal today is how do we find the rate of increase? Okay, how fast is our balance increasing at a particular moment in time? So here's just one example. So suppose you invest, I'll just make up a number, $5,000 into an account paying 5% interest compounded continuously. And then I'm going to give us 3 parts. Part A is going to be find a function giving your balance after t years. Should say balance, sorry. So we're going to use our model over here. Part B is going to say find the balance after 10 years. And then part C is going to be how long will it take your investment to double? So for part A, let me just make sure everybody's for the most part caught up before I get to this next step. Okay. So, part A, find a function giving the balance after t years. So we're looking for a function b of t. And remember, that's going to be your principal or initial investment times e to the rate times the power of t. So what was our principal this time? That's the initial investment of 5,000. And then it's going to be e to the rate times t. Now you have to be careful. Typically the rate is usually not given as a percent. Anybody know how to fix that? Yeah, we always convert the percentage interest rate into a decimal. And you always take the decimal after the if it's in percent form, you take the decimal and slide left 2 units. So as a decimal, the rate is 0.05. So you get 0.05 t in the power. And then for part B, what do I do now if I want the balance 10 years later after that initial investment? We'll just plug 10 into the function. So the balance after 10 years is b of 10, which is 5,000 e to the 0.05 times 10. And we'll probably, let's approximate that to 2 decimal places. Rounding an amount of money to 2 decimal places always gives you to the nearest cent. So when I do this on my calculator, this is really 5,000 e to the 0.5 times 10 slides the decimal place 1 to the right. And what your balance is going to be is $8,243.61. So it takes 10 years for the investment to grow an additional $3,243.61. So for part C, how long will it take the investment to double? It's certainly going to take more than 10 years, right? Because at this point it hasn't doubled yet. Okay. So we should get something greater than 10. All right, so anybody have an idea on how to start this question? Okay. Is that what you were going to say, Ollie? Okay. So yeah, Amanda's suggestion was we'll take our function for the balance, we'll set it equal to 10,000. I like that idea. And then what do we want to solve for? Yeah, you want to solve for your exponent t. Now, if I do need any properties again, I will let you know. There was technically one thing I forgot to write, and that's what's called the conversion. So, to be able to solve this, you can either use a conversion to logarithmic form or you can use the inverse properties. So actually I didn't really even need to write this conversion, but some of you might like this better. So if you have an exponential expression like we do and you're trying to solve for the variable and the exponent, the power is always equal to log. The base of the exponential stays the base of the log, and then the output becomes the input. This is coming from the fact that exponential base b and log base b are inverses of each other, so the inputs and outputs swap when you go over to the inverse. We're not really going to do a whole lot with inverses in this class. And then the other fact we could use, and this is what I'm going to use, is I'm just going to use the inverse property log base b of b to the x equals x. So you could use either one to solve this. Okay. So let me just wait a minute. So first of all, if I want to solve now for t, anybody know what the first step would be? Okay, so you're going to divide by 5,000. You always try and isolate the basic exponential piece first. So if I solve for 5,000, you get e to the 0.05t. 10,000 divided by 5,000 gives us positive 2. Okay. Now, at this point, you can either do the conversion, or you can use the fact that if you apply a log to an exponential at the same base, you just get the power back. Usually that's what I do. So what I'm going to do is I'm going to take ln, or natural log, of both sides. Okay, so natural log of e to the 0.05t is equal to natural log of 2. And then now this is my power. Does anyone remember what natural log really denotes? Like natural log of a number, it's really log with what as the base? E, right? ln of x is this notation for log base e of x. So I'm doing log base e of e to a power. So what do I just get back there? You just get your power 0.05t. And finally, when you solve for t, it's going to be natural log of 2 divided by 0.05. And I'll round this to just 2 decimal places. Anybody done that yet?
13.86.
You have 13.86. Okay. So just over 13 3/4 years and less than 14 years. So yeah, if you want your investment to double, you've got to wait 13.86 years. And does that kind of agree with what I was saying for part B? The balance hasn't doubled yet after 10 years, right? We know it's going to double sometime after 10 years. Okay. So essentially, I think ultimately that's all we're going to need to know. So I just wanted to real quick go through an example of compound interest, how to form the model or write down the function, how to evaluate it, and then how to find the amount of time it takes for your investment to reach a certain point. Okay, so now what we're going to do is, now I only have maybe 9-10 minutes. I should have time to maybe do the derivative of e to the x, and then maybe do this example. We'll see how far we get. So not all exponential functions have base e either. So we'll do e to the x first, and then I'll tell you what derivatives of, say, b to the x is for any other base b. Okay. Is that okay with everyone? Was that a somewhat decent refresher on continuously compounded interest? Okay. So what we're going to do is, we don't know what the derivative of e to the x is. If you don't know what the derivative of something is and you don't have a rule for it, what do you probably have to fall back on to find its derivative? Some algebra will be involved, but ultimately, what was the definition of a derivative, right? We're going to have to use the limit definition. Okay? So if I want to do the derivative, if I want to do the derivative with respect to x of the function e to the x, what we're going to do is we're going to take the limit as h goes to 0 of the function evaluated at x plus h minus the original function divided by h. And then here's where the algebra comes in. So we'll have to try and simplify the difference quotient algebraically. So here's where some of our properties of exponents come in. So, and as I promised, let me remind you of them as I use them. So one thing I can do is if I take an exponential expression with a sum in the power, it can be rewritten as a product of exponentials. So where do you see something like that? Well, you have an e to the x plus h. So the first thing I'm going to do, still have the limit as h goes to 0, that becomes e to the x times e to the h minus e to the x over h. So I split up the e to the x plus h as e to the x times e to the h. Because if I want to go backwards, I just add the exponents and I get where I started. Is that all right? Okay. Now, is there anything in common in the numerator that I could factor out of the numerator?
E to the x.
Okay, so both terms have an e to the x. So I have e to the x times e to the h minus 1 left over, divided by h. Now I've got to remind you of another fact. We learned a while ago that the limit as x approaches a of a constant times a function. Anybody remember what we can do with this constant?
Pull it up.
Yeah, just like a derivative, you could pull the constant out front and then just take the limit of the function f of x itself. Now, what variable does this limit depend on? Right? This is just depending on the variable h. So since this limit only depends on h, e to the x is really a constant. Okay, so the e to the x can come out front, and then the limit that we're left with is the limit as h goes to 0 of e to the h minus 1 over h. So here's something that's really interesting. Well, let people get caught up first. We'll figure out what that limit is in just a moment. So it turns out the derivative of e to the x is proportional to itself. So the derivative of e to the x is going to be some number times e to the x. Okay. So I'm going to come over to the side here, and we're going to make a table because we don't have any tools to solve for this limit by hand. Okay. There's no way to, essentially there's no algebra that we can do to cancel that h in the denominator. So what I have to do is I have to inspect this using a table where I have h values getting closer to 0, and then we compute what the values of e to the h minus 1 over h are. I'm only going to do it from the right, but the right and left-hand limits end up being the same. But I'll start with, say, 0.1, then we'll do 0.01, 0.001, and if necessary, we'll do one more. Okay, so my h's are getting close to 0. Let's see what the function of h gets close to. So some of you, maybe if people that have calculators over here could do the first two, and people over here could do the second two. Okay, so on the left side, just go ahead and do the first two h values, plug them in, and then if people over here could help me do the rest. So I got the first one. It ends up being 1. I'll go 3 decimal places. 1.052. Anybody got the second one yet?
1.005.
So that's 1.005. How about over here? Anybody do the third or fourth one? What'd you get for the plugging 0.001 into that?
1.0005.
So how many zeros? 3? Okay. My guess is it just keeps, if you look at the pattern, you just keep throwing an extra 0 between the decimal and the 5. So this would be 1.00005. Okay. And I could get closer and closer to 0, but what does it look like this limit's getting closer to? 1. So a fact, and again, we don't have the tools to do this, but the limit as h goes to 0 of e to the h minus 1 over h just equals +1. That means, and this is kind of interesting, the derivative of e to the x is e to the x.
Weird.
It is. That means, that's kind of interesting. If you look at the graph of e to the x, it's an increasing exponential that looks like this. whatever the value is at a particular point is the same as the slope of the tangent line there. So the value of the function and the slope of the tangent line are the same. I don't know, whatever the slope of that tangent line would be. Okay. I don't know if my picture is that great, but if this is A, the slope of the tangent line is A. Okay. So yeah, that one's kind of strange. Now, for the other ones, and we'll do a couple examples tomorrow, I'll tell you the derivative for general exponentials, and then we'll revisit our continuously compounded interest problem. The homework is open. If you want to read ahead in the book and look at a couple examples to get started on the online and written homework, go for it. We'll finish this tomorrow, review Friday, test Monday.
That'll be joyous. Are you coming to school tomorrow still?